Hello, in this video we'll be looking at further stress-strain graphs. Now in my previous video we looked at the stress-strain graph for ductile material. I chose steel as an example. That is a poor example because copper would have been a far better example because steel can be hardened. And if you've got hardened steel, a process in which you heat it slowly, then quench it in cold water, it becomes brittle. Okay, and a stress-strain graph for a brittle material, such as hardened steel. Okay, so I'm going to use these symbols here: stress and strain. Well, simply it'll follow Hooke's law, a nice straight line, and then suddenly it'll get to there and it will fracture. So that's stress against strain. Okay. Now let's also look at one for rubber. Rubber is clearly elastic behavior. Now for rubber, we'll find a stress-strain curve will look like this. I'm going to write the word stress-strain to help you remember those symbols. For rubber, a stress-strain curve will look a bit like this. So we will have, this is loading, by stretching it, and this here is unloading. So loading up there, and this is unloading. Now, for our simple steel there, until it breaks, of course, the area under the graph there, which would be half of the stress times the strain, or if you like, you'll find that this is the energy stored per unit volume. Okay, so the area under the graph is all to do with energy stored. So here it is simply that area there, wherefore, as you see for the rubber, you see it'll be the area stored under there is different to the area stored in there. So the space in there, all this energy there, that will be lost as heat, and the rubber will heat up. Okay. And one more graph I'll draw. I shall draw a graph of a stress-strain graph for polythene. Okay. And the stress-strain for polythene looks like this. Polythene will behave like this. So stress against strain, and you'll find it looks like this. Goes up, a little curve there. So this is your loading it. Now it's permanently stretching there, and you see that when you've unloaded it, it will suffer from permanent strain. So if it suffers some permanent strain, that means the extension divided by the original length, so therefore strain is equal to the extension divided by L, which is the original length. So this is changed, so therefore the material has been permanently strained, and effectively it has changed length. The molecules, the atoms, well, the molecules in the fact of this will no longer go back to its original position.